Yes. Good morning, class. Good to see. Good to discuss with you again. So this morning we want to quickly um, let me speak further on the note I gave you the last time. I believe that most of you opened the notes and you saw what is there. Now quickly, I still feel I should talk about how convex lens and the concave lens, how they form image of objects placed in front of them. There are rules that we follow to construct this diagram. These rules that I'm going to talk about now, they are similar to what I told you when we were discussing concave mirror. So on the screen here, you are seeing the diagram of a convex lens. This is the diagram of a convex lens. Okay, so you are seeing ray 1 and ray 2. To construct ray diagram, you need at least 2 rays from the luminous object. It can be 3. It can be 3 rays, but you need at least 2 rays. And there are conditions or rules that we must follow for us to construct the diagram. If you look at ray 1, it's got that ray 1 is parallel to the principal axis. And you also see that ray 2 is passing through the optical center. Now, there's this straight line that passes through the optical center of the lens. This straight line where we have F and 2F is called the principal axis. So you discover that at one side of the lens we have 2F and F. At another side we also have F and 2F. Okay, it means that the lens is symmetrical on both sides. Okay, it's also by convex. So we expect that whatever you measured on one side of the lens, you can also measure at the other side of the lens. Now back to the rule now. So rule 1, any ray of light that is part of the principal axis must be refracted, okay, through the principal focus. You can see that that's ray 1. Now ray 2, you can see ray 2 is passing through the optical center and is doing that undeviated. It is continuing in that straight line. So where the two of them intersect, you have the object formed. So the first case where we have the object placed beyond 2F, the image will be formed in between F and 2F. The image will be a real image. That is, if you place a screen there, you're going to see it on the screen. It will be an inverted image, and then it will be diminished. That is, it will not be as the same size as the object. That's our case number 1. What you are seeing here, they are the result of experiment carried out. So if you come to the laboratory, pick your convex lens, place your image at a distance beyond 2 times focal length of the lens, you're going to locate the image in between F and 2F. That is, if you place the object beyond 2F, the image will be in between F and 2F. Now case 2. In case 1 we have the object beyond 2F. Now in case 2, we have, let's look at this number 3. I'm coming back to number 2 up here. Number 3 here, we have the object placed at at 2F. Okay, we are moving from beyond 2F to 2F. So when you have the object at 2F, where would the image be? Once again, ray 1 parallel to the principal axis is refracted through the principal focus on the other side. Ray 2 going through the optical center is going through it in that straight line. Where the two of them intersect, you have the image. So if you are told to construct ray diagrams, these are rules that you must follow. You don't just draw any lines anyhow. Anyone that is part of the principal axis must be refracted through the principal focus, and anyone that passes through the optical center must go through undeviated, unrefracted. So it continues in that straight line. So we need just 2 of these rays. Where they intersect, we have the image formed. So when the object is placed at 2F, the image will definitely be at 2F. It is a real image. At least you can see it on the screen. It is inverted. It is the same size as the object. That's our case 2. So we are moving from beyond 2F to 2F. Now we are moving from 2f to a position between 2f and f. That is in number 2 above here. I've explained. Number 3 is what I just explained now after number 1. So I'm coming to number 2. Number 2 is what you see up here. Number 2 is above number 3. Okay, and beside my very good, you can see number 2 here now. So here in number 2 we have the object between 2f and f. As you can see, the two rays are still, one of is still parallel to the principal axis and is refracted through the principal focus. The second one passing through the optical center. Where the two of them intersect, you have the image there. So you observe that the image here now is bigger than the object. So the image is magnified. The image is inverted. The image is real. And the image is formed beyond 2f. Please take note of all of these points. Very, very important. Now, let's look at another case. Another case is what we have here in number 4. You know, we're moving the object gradually. Okay, from we have moved from 2f, okay, to 2f. We have moved from 2f now to a position between 2f and f. Okay, so we are looking at another position now. That is when the object is, okay, let's look at this. Okay, let's look at when the object is now placed at f. When the object is placed at f, where will the image be? So the image will be formed at infinity. That is, the image, you will not see it on the screen. Is formed at a position that we cannot say precisely that this is the position. Okay, so that is when you place the object at f. I want to go back to when you place the object at a position between 2f and f. Okay, we have okay, sorry, let's go to when the object is placed beyond the 2f. The image is a diminished image and is formed between f and the 2f. So the last one I've just spoken about now is when the object is placed at f. So when you have it at f, the ray of light, okay, will not intersect. Okay, they are parallel rays of light, and so the image formed will be formed at infinity. It will still be a real image, okay, but it will be formed at infinity. Now the next position is when the object is now placed between f and the optical center, between f and the lens itself. So you can see the object here. So when that happens, the image will not be seen on the screen again, but you can see the image through the lens. So the image formed will be a virtual image. As you can see, the image is right behind the object. So the image here is erect and it is magnified. It's a virtual image. Okay, that is, so it means that a convex lens can form either a real image or a virtual image, but it can only form a virtual image when the object is placed between the principal focus and the optical center of the lens. That's when it can form a virtual image. So that means that for you to get a real image, it depends on where the object is placed in front of a convex lens. And if you must get a virtual image also, it's still a function of where you place the objects. Now the other type of lens is the concave lens. Now this concave lens, it does not matter where you place the objects. Okay, as you can see, I said an object placed at any position in front of a convex lens produces a virtual, erect and diminished image. That is, this one, it doesn't matter where the object is placed. For a concave lens, A concave lens is a diverging lens. So it doesn't matter where you place the object, the image is always a virtual image. At least you cannot see the image on the screen. You're going to see it through the lens itself. Alright? And then it will be diminished, and then it should be upright. So those are the ways we form images of different objects placed in front of either a concave lens or a convex lens. Now, there are quite numbers of ways we apply this convex lens. Before we go to the application of a convex lens, we can solve problems as regard where an image should be and where an object should be in front of either a concave lens or a convex lens using the mirror equation. So if we are going to use the mirror equation, okay, that is, we can find by calculation where the image of an object placed in front of either a concave lens or a convex lens will be. Now let's look at this example here. The example here says a converging lens produces a 4 times magnified and upright image. You know, a converging lens is a convex lens. So let's look at the question again. A converging lens produces a 4 times magnified and upright image of an object placed in front of it. If the focal length of the lens is 11 centimeter, calculate the object distance. Calculate the object distance. Alright, so let's look at what are we given in this question to be able to calculate the object distance. Number one, they have mentioned the magnification of the look at it again. A converging lens produces 4 times magnified and upright image, okay, of object placed in front of it. So the magnification here is 4. Okay, that is, the image is 4 times the object. That is the meaning of what we have here. Okay, so the focal length here, according to the question, is 11 centimeter. So we are calculating the object distance. Alright, so since we were told that it's an upright image, from the diagram I showed you earlier, you discover that for a convex lens, the only case where we have an upright image is when the image is a virtual one. So the other images that we saw were real images, okay, and we usually differentiate between a virtual image and a real image. We usually attach a negative sign to a virtual image and a positive sign to a real image. That is, if you are using what we call real is positive. Okay, so if we say real is positive, then the virtual image will be negative. Now, this equation 1 over v plus 1 over u is equal to 1 over f is also called the mirror equation, and is useful here also. So from the question that we have here, our f, which is the focal length, is 11 centimeter. Now the image is 4 times the object. That means if the object is u, then the image is 4u. That's the implication. So if you come back to the equation here, since it's a virtual image, our image will be negative. That's why you have 1 over minus v plus 1 over u is equal to 1 over, it's supposed to be 11, because in the equation we have f to be 11. So, but never mind. So if we find the LCM on the other side, what we're going to have will be 3 over 4u equals 1 over 10. So at the end of the day, we have our object distance from that calculation. I believe you are okay with that explanation. Okay, now there's another question here. This one is saying find the nature and position of the image of an object placed 6 cm from a diverging lens of focal length 15 cm. A diverging lens is a concave lens. Because a diverging lens will always form a virtual image, the image is always negative. And the focal length of a diverging lens is also negative. That is why we have f here to be minus 15. You know, they gave us the focal length in the question. So we attach minus because it's the focal length of a diverging lens. It's going to be negative. The object distance is 6 cm. So you may be wondering, where do we get this minus from? The minus sign is because a diverging lens always forms a virtual image. So its focal length also is negative. So using 1 over v plus 1 over u equals 1 over f. Now, because here now, we have to find the image and the nature of the image. So we are not going to bring the minus sign for v at the beginning of this equation. So it is the final answer that will confirm that the image truly is a virtual image. Because if we start to use minus from the beginning here, at the end of the result, its result might contradict what should be in the real sense of it. But if you look at the first case I gave you, they have given us the image distance already. So that's why we're not actually finding the image distance in that case. That was why we used minus from the beginning. But in this second case, where we have to determine the image distance, we will not from the beginning use a negative sign. Okay, so it is the result that it will confirm that it is a virtual image. Okay, so using real is positive now, we are going to have, since f is minus 15, so we have, and u is 6, so we are going to have v will be minus 1 over 15 minus 1 over 6. So simplify and obtain your v from this. Just substitute for f and u, so you can obtain your image distance from there. And you observe that what you will get as your image distance will be a negative value, and that will tell you about the nature of the image, that the image is a virtual image. Okay, now there's another example for you here. So if you look at this example here, we say an object placed 5 cm in front of a converging lens of focal length 10 cm produces a magnified image 8 cm high. Find the size and the position of the image. So what kind of type of lens is this one? It's a converging lens. Okay, they have given us the focal length to be 10 cm. They have mentioned the magnification. Okay, produce a magnified image 8 cm high. Then find the size and position of the image. Okay, very good. So if you come here, we already have object distance and we have the focal length, so we can obtain the image distance. So the image distance here, after we have substituted for u and f, is minus 10 cm. That simply means that the image formed is a virtual image. Okay, now, but don't forget that we are told to calculate the size and the position of the image. What we have just found now is the position of the image. We have not found the size. Okay, so now let's come back to what is magnification. Magnification is the same as image height over object height. It's also the same as image distance over object distance. Okay, it's the same as image distance over object distance. So if we bring the image distance that we have just obtained now to be 10, we're not carrying that minus over here, because the minus here is only telling us about the nature of the image. It's a virtual image. So in the next calculation now, you don't need that negative sign here. So you just need the absolute value of that image distance. So in this case, we have image distance is 10 and object distance is 5. Then the image height. Okay, I guess there's a problem with the question here. Okay, in the question, it said the lens actually produces a magnified image 8 cents. So they have given us the image height. So what I'm sure they want us to find in that question is the object height, not the image height. So we can come back and find the object height here, and then that will be 4 centimeter. So thank you very much. And then what I want you to do, very very important here, before we come back and discuss the applications of both concave and convex lens, I want you to, number one, as an assignment, you will send it to me via WhatsApp. I must still say that most of you, your response to assignment is not encouraging. So you will construct the ray diagrams that we have mentioned. You know, we for convex lens, we have about 5 positions for the object and the image formed. So I want you to construct each of them and then send it to my WhatsApp group, my WhatsApp private chat room. Then, as an assignment, I want you to also find out what is define what we call short-sightedness and the long-sightedness, and how each of these can be corrected. That's number 2 assignment. Number 3 assignment is to write the similarities between the human eye and the camera. Human eye and camera similarity, okay, and the differences. Thank you very much. I'll see you next time. Bye.